we're going to talk about what's called a motional EMF. So I have a conductor. So think of it being like a part of a wire. It's of length L, and we're going to push it so that it moves with a constant velocity V through a uniform magnetic field that's pointed into the plane of the page. We're going to see that sort of like with the Hall effect, making the conductor move through the magnetic field is going to cause a charge separation. And so the two ends of this conductor are like the terminals of a battery. So first, let's think about the direction of the magnetic force on the electrons in the conductor. So V is going over to the right, B is into the page, so V cross B points up the page, and we're talking about the magnetic force on electrons, so the magnetic force is going to point down the page. So inside this conductor, there is going to be a magnetic force because the conductor is moving through a magnetic field. That magnetic force is going to cause the negatively charged electrons to deflect down to the bottom, and we'll have the absence of electrons, or positive charge, at the top. So just sort of denote that in cartoon form. The positive charges are going to be at the top, and we're going to have negative charge at the bottom. And that separation of charges is going to grow until the Coulomb force from the electric field in the conductor cancels out the magnetic force. So there is our Coulomb force arising from an electric field that's pointed down in the conductor from the positive charge and ending on the negative charge. So think about how big that electric field is going to be. When the Coulomb force is balancing out the magnetic force, we'll have a net force of 0, which is made up of the part Q times the electric field plus Q V cross B for the magnetic force. Q is multiplying both of those terms, and the sum of those terms is equal to 0, so I can just get rid of the Q. We'll have that the electric field is going to be equal to minus V cross B. If we look at magnitudes, the magnitude of the electric field, well, V and B are perpendicular to each other, so E will equal the speed of the conductor times the strength of the magnetic field. We also know that we can think of that electric field as being a change in potential over a change in distance. And I should put absolute values there because we're talking about the magnitude of a vector. This tells us, thinking of this potential difference across the two ends of the conductor, We think of that delta V as an EMF. That EMF is going to be the speed times the magnetic field strength, and then we have the length of the conductor, L. And that is a motional EMF. Conductor moving through a magnetic field is going to have an induced EMF across the conductor. And this EMF exists because the magnetic force on the charges in the conductor are going to deflect charges, and that charge separation is going to continue to build up until the Coulomb force cancels out the magnetic force.